All right, let's get this going. Have an easier class today. In terms of introducing new theory, almost nothing. It's just going to be a bunch of example problems almost. So the only piece of theory that we have to introduce today is something called the chain rule. So let's remind ourselves of some of our basic rules for taking a derivative. So first off,
Power, quotient.
well, I'll try and remember the same order I did last time just to help trigger everything. So what's the derivative with respect to x of 7, a constant? 0. Derivative of a constant, always 0. Okay, what's the derivative with respect to x of something like x to the n?
It's n subtract 1 and down to x.
N times x to the n minus 1. Good. Okay. And then we had our sum rule. We don't need to write that one out. The derivative of a sum is the sum of the derivatives. That one's intuitive. But let's think about the product rule now. What if I have the derivative with respect to x of two functions, u times v?
That's a product one.
Yeah, it's a product rule. What was our product rule?
Was it your high low or was that?
No, that's your quotient
that's
rule.
quotient.
Because you have to have a high and a low.
Alright.
Was it
Come on.
du over d of v?
Du, okay, you could be saying it. So you're saying it's the derivative of u with respect to v.
Oh.
Sorry.
Oh.
No, du dx, yeah. Oops. No, we're not taking derivatives with respect to v. I don't know why.
Oh.
We're taking our derivative with respect to x. So what is it?
It's the first times
First
the derivative of the
times the
second,
derivative of the second
plus the second times the derivative.
plus the second times the derivative of the first.
Oh.
And that's pretty much the mnemonic used.
Yeah, okay.
People will also say the derivative of the first multiplied by a second plus the first times the derivative of the second. Logically equivalent.
You just threw that in my mind.
What?
Never mind.
Okay. And then finally we had our product rule. So the derivative with respect to x, this time we have a product of two functions, u over v. Trying to show that those are both functions in terms of x. So what was that one?
That's
That was your
What's the mnemonic?
High d low.
Low d high.
Oh, it's low d
So low times the derivative of the high.
yeah.
Low d high.
that's quotient, not minus.
That's a quotient.
You
Minus.
said
Minus
product.
your
I
high
use
low.
Minus high d low.
Low and square and off we go.
Square what?
Square the
Square
bottom.
the
V.
bottom.
Right?
Square the bottom. Square the bottom. And away we go.
High is it's low d high minus high d low. square
Low
the
d high minus high d low. Square the bottom. Away we go.
Okay.
D high.
Okay. So now we got to introduce, I was going to say our last standard rule for calculating derivatives. And that is going to be the chain rule. What's the chain rule? It's, well, we have it right here. We're going to prove that the derivative of f composed with g at some point x naught is equal to the derivative of the outside times the derivative of the inside, is how you'll remember it. The product rule, or the chain rule, you do the derivative of the outside times the derivative of the inside. Another way to think about it is the derivative, if y is a function in terms of u, and u is a function in terms of x, then the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. So that can be a lot to take in, because for some reason we just don't think well about function composition. It always confuses us. So we're going to do a concrete example, then go through the proof to give you a sense of what this is saying.
Okay.
So we'll pick one of these. We'll pick the first one. So I'm going to calculate the derivative of this. Now you already know how to calculate the derivative of this, right? Here's our y. How would you calculate the derivative of that right now?
Take the derivative of...
Well, first you have to square it all out,
Yeah.
right? So you would write y is equal to, let's see, that times that is going to be 9x to the 4. That times that is 3x squared. That times that is another 3x squared for 6x squared. And then finally 1 times 1 is 1. So y is equal to that when we square it all out, right?
Yeah.
And now the derivative of y with respect to x, or y prime, same thing, right?
Yep.
Throw all the different notation at you to make sure you don't forget. Is going to be equal to what?
36x to the power of 3 plus
36x cubed plus what?
12x.
Plus 12x plus
0.
0. The derivative of that plus the derivative of that plus that, or the derivative of that.
Yep.
Okay. Now I'm going to use the chain rule. When I use the chain rule, I have to think about it as a function inside of a function. So I'm going to think about this function, y is equal to f of u, where u is equal to some different function, g of x. Let me say this a bit differently so that we can see our notation here. So rewriting this function,
Okay.
this function is, I can think about my f of x, I'll call it f of y here. My f of y is equal to y squared. Notice it's squaring something.
Yeah.
Where, how should I write this? Let's see, my notation over here, I had an f, okay, y squared, and then I'll say g of x. I'll say y is equal to g of x is equal to what we have inside. 3x squared plus 1. You see that?
And the y square encapsulates.
Or maybe you just be okay with this. Let's say f of x is equal to x squared. Audrey. Yeah, this is how it should have written. Okay, I think that this will help keep it the course for now. G of x is equal to 3x squared plus 1. Now notice that what we have up here is f of g of x. So here's f of x, here's g of x. What is f of g of x equal to? It's equal to what we get when we plug this into this.
3x cubed plus x squared.
So it's 3x squared plus 1 all squared, right?
Yeah.
So if this is our f of x and this is our g of x, then this is f of g of x.
Yes.
So the trick with these is you see that this is a function inside of a function.
Okay.
You with me? And now, so what is the derivative of this? What is the derivative with respect to x of f of g of x? That's the same thing as asking what is f composed with g prime of x. Same thing. The derivative of that, or compose them and take their derivative. So that's what that notation means. Same thing, right? And what our rule up here is saying is it's the derivative of the outside times the derivative of the inside. So it's f prime of g of x times g prime of x. So if this is our if this is our f of x, what is f prime of x?
2x.
And what is our g prime of x?
6x.
6x. So this is saying that our answer is f prime of g of x. So plug g of x into here. So it's going to be 2 times our g of x, which is 3x squared plus 1. All times g prime of x is 2x.
Where do you get that to?
6x.
So I plugged in g of x here. What is f prime? What is f prime of g of x? It's what I get when I plug g of x into f prime of x. Plug this in there, and you get 2 of those.
Okay, yeah, I see that.
So f prime of x times f prime of g of x times g of x.
G prime of x.
So
is
where's the
6x.
normal f of x?
Here's f of x,
Why is
here's
it
g of
doing
x,
that?
here's f prime of x, here's g prime of x.
Why doesn't the chain rule use that? All three.
It does. Doesn't it?
No, it only uses f prime, g of x, and then g prime.
Oh, because f doesn't show up in its own derivative.
Oh,
Okay, so here's the derivative. Let's multiply this out and see what we get. So we get,
That's supposed to be 6x, by the way.
this one is?
Yeah,
G prime of x.
Thank you. That's why the numbers weren't coming out. Okay, so let me really quick just combine the 6x with the 2 over here. So we get 12x times 3x squared plus 1, right?
Whoa, why are you able to combine the 2 and the 6?
You can multiply in any order you want. I can multiply this to this first, or I can multiply this to this first.
I know, but the 2 and the x can combine because it
What's 2 times 6?
12.
if I have 6x 2 times, what do I have?
Oh, that's strange.
Okay, so it's just 12x. When you multiply terms, you multiply constants by constants and variables by variables.
I think I got screwed up on combining my terms then.
Okay, so anyways, here it is. Now multiply it out. 12x times 3x squared is going to be 36x cubed. 12x times 1 is plus 12x. And do we get the same thing?
Yes.
Yes. So it gives us the same result. Now, when you first look at that, you're going to think that the chain rule is way, 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 way more convoluted. Right?
Yeah.
But here's how we wouldn't label all these things. I'll label them a few more times for you as we do examples to help you get used to it. But here's how a sane person would have done it. They would have started out with 3x squared plus 1 squared. And so I look at it and I say, look, that's this function squared. So take the derivative of my outside function, which is just something squared. So that brings down to 2. And so I get 2 times that something, all to the 1 now. And now multiply by the derivative of the inside. And what's the derivative of the inside? 6x. So no one goes through the time of labeling it all this way. You just look directly at it and say, take the derivative of the outside thing and multiply by the derivative of the inside thing.
Take the root and
Oh, what the
multiply
heck?
by
The derivative of the outside multiplied by the derivative of the inside is the mnemonic you will use to remember how to do the chain rule.
Isn't that just 12x?
This?
The derivative of the outside times the derivative of the inside.
So the derivative of the outside, we have something squared.
Yeah.
How do I take the derivative of something squared? I bring down the 2 and replace it with a 1. Now times the derivative of the inside. What's the derivative of this thing?
6x. And you're timesing it by the 3x squared plus 1 too. So you're going.
Well, here's my answer. This is exactly what we have written right here. So I'm showing you that this is how you actually go through the process of calculating using the chain rule. No one actually labels everything like this. Occasionally it's helpful in a particularly difficult problem, but outside of that, it's pretty straightforward. And anyone who came across this problem, who was exposed to calculus, would have gone to the chain rule way faster than the product rule.
Yeah.
Or way faster than distributing that out and then calculating the derivative. Because now, imagine that you had something like, let's do one more example to show why this is so useful before we go through the proof. Let's imagine this time that I gave you, we'll jump ahead to this one. So let's look at f of x is equal to 5x cubed minus x to the 4, all to the 7. You want to multiply that out?
No.
How many terms are you going to have if you multiply that out? 128. If you multiply all that out,
Okay.
right?
Yeah.
I don't want to deal with 128 terms. That sounds like a nightmare. So I'm just going to use the chain rule. So f prime of x is going to be the derivative of the outside. Let's see, what is that? Bring down to 7. 7 times whatever we have, whatever I'm viewing as my internal function, is now to the 6, times the derivative of the inside, which would be
15x squared
15x squared
minus 4x cubed.
4x cubed. But yeah, you got the right idea. And there we go. Look how easy it was to calculate that derivative. What would have been a nightmare before?
Why?
That's still, you gotta simplify that though.
You gotta simplify that though. But I can take this and simplify it and solve 5 more problems like this before you'll finish expanding this thing out.
That's true.
Ow. So.
Huh?
Never mind.
Do you know what I mean by expand this thing out? What is this equal to? What is f of x equal to? It's equal to 5x cubed minus x to the 4 times 5x cubed minus x to the 4 times 5x cubed minus x to the 4. And I can only write 3 of them. Got to write that 4 more times. And then I got to distribute this into this, and then distribute those into that, and then distribute that into that.
Yeah, I got you.
And if you don't combine like terms as you're going, when it's all said and done, you're going to have 128 terms. And then you can combine your like terms, it will reduce however many terms it reduces to. And then you can calculate your derivative. Or, you can just calculate your derivative here. And in fact, you don't even want to multiply this out because it's already factored for you.
Oh yeah, it is. So you should leave it like that.
You should never multiply out something like that to calculate your derivative.
I'm saying for your f.
Oh, yeah, that is a perfectly good answer.
Okay.
The only thing I would change is, as a matter of practice, you either make your exponents increasing or decreasing. So I probably would have written that before the x to the 6th one
Whoa.
in my final answer. But let's nitpick it.
Oh, okay.
Okay.
And I definitely would not dock you for that being your answer.
I like the chain rule.
Yes, the chain rule is fantastic. It's amazing. We love the chain rule. It's of the rules, the one that's the hardest one to use, and the one that you're going to forget to do correctly the most frequently. So let's go over now the proof of the chain rule. So, if g is differentiable at some point x naught, and f is differentiable at the point g of x naught, because remember, we're going to have a function inside of a function.
Yeah.
So f is going to take g as its input. So g is differentiable at x naught, and f is differentiable at f of g of x naught. Then the derivative of f of g of x naught is going to be the derivative of the outside function, f prime of g of x, times the derivative of the inside function at that point.
Yay. Okay.
So that's what we're trying to prove. Now, set it up, let g be differentiable at x naught, and let f be differentiable at g of x naught. So assume that these functions actually have derivatives at this point, we're going to prove that this is the derivative then of the composition. Now, we have to remember something from last week. We proved that if a function is differentiable at a point, then it is continuous at that point. And so we have to use that fact. So since g is differentiable at x naught, then I know that g is continuous at x naught. And what does it mean for a function to be continuous at a point?
Its limit is equal to its output.
The limit of the function at that point is equal to the value of the function at the point.
At that point.
So that tells us that the limit as x approaches x naught of g of x is equal to g of x naught.
Yes.
That's what it means to be continuous. So I now know this limit. What am I trying to do? I am now going to calculate what is the derivative of f composed with g of x naught. What is it? Just using our definition, it's the limit as x approaches x naught of what we get when we plug x into our function, so f of g of x,
Okay.
minus what we get when we plug x naught into our function, so f of g of x naught, all over x minus x naught. That's just flat out the definition of a derivative so far. Forget that part.
Yeah.
You with me? Now I'm just going to multiply top and bottom by the same value here.
Okay.
Now, there's a technicality that we're not going to deal with in this proof. To really prove it full is something you do in a real analysis course. We're ignoring the fact that g of x could be the same thing as g of x naught. And so we could have, right here, just barely multiplied by 0 over 0, which is not valid. So we're going to assume that you can ignore that one point and everything still works. It does, but we're not going to prove that it does. So one technicality with the proof. Okay. But now we multiply it top and bottom by the same thing. And so now all I want to do is write this denominator over here and this denominator over here. I'm using the fact that a over b times c over d is the same thing as a over d times c over b. I'm just going to swap my denominators, who cares?
Yeah.
Because in our product, we still account for everything. So, I swap my denominator, so I'm going to put this denominator with this term and this denominator with this term. You with me? That's what I did there, and I'm going to split it up into two separate limits, because the limit of a product is equal to the product of the limits.
Okay.
Okay. Now, up here, what did we say? We said the limit of g of x as x approaches x naught is g of x naught.
Yeah.
Let me say that in different language. As x approaches x naught, g of x approaches g of x naught. So the limit as x approaches x naught is the same thing as the limit as g of x approaches g of x naught. Those are saying the same thing. And so now I have the limit as g of x approaches g of x naught of this thing times the limit as x approaches x naught of this thing. Now what is the limit as x approaches x naught of this thing?
It'll be divided by 0, 1.
What is this the exact definition of?
The derivative.
That's the exact definition of the derivative of that function at the point x naught.
Yeah.
That's precisely its definition.
Oh, I
And
see.
now notice, slightly more convoluted, but it's the same thing. We're taking the limit as our x term approaches our point of f of our x term minus f at that point all over our x term minus the point.
Yes.
So this is saying the exact same thing as this, right?
Yeah.
So this is the exact definition of the derivative of f at the point g of x naught. So that is f prime of g of x naught, and that is g prime of x naught.
Okay, that makes sense. Sweet.
Okay, going to be a little bit less precise. Walk you through the same proof now using Leibniz notation. Different notation you've already seen, but just different way of saying the same thing. So this time I'm going to think about y is equal to some function in terms of u,
Okay.
and u is equal to g of x. So y is equal to f of g of x. Same exact thing, just going to use slightly different notation.
Okay.
With me?
Yep.
Okay. So then, what am I going to prove? I'm going to prove that the derivative of y with respect to x, remember, what is y? It's our whole function. Y is equal to f of g of x. F of u or f of g of x. So I'm going to prove that the derivative of our whole thing with respect to x is equal to the derivative of the first function, the derivative of y with respect to u, times the derivative of our second function, the derivative of u with respect to x.
Okay.
Make sense? And I'll do another example relabeling this way instead of this way so you can see how it does the exact same thing. Okay. So first thing we're going to notice is g of x here, once again we're assuming it's a continuous function. Right?
Yeah.
Yeah.
So here's u. U is some function. U is equal to g of x, so here's our function g. And if you pick some point there, then as, well, 2 points. So this right here, sorry, really scratching this fast, is our delta x. And up here is our delta u in this case.
Very good.
Because we said u is equal to g of x. So as our delta x gets really, really small, our delta u gets
Small.
really, really small. And that's the case because it's a continuous function.
Right.
That's going to be the case with continuous functions. And so, as delta x approaches 0, delta u also approaches 0. In other words, I'm going to say the limit as delta x approaches 0 is the same thing as the limit as delta u approaches 0.
Okay.
Those are going to be logically equivalent. Same type of thinking we used up here in swapping from here to here.
Yeah.
Same thinking, slightly different notation. Okay, so now let's calculate it. What by definition is the derivative of y with respect to x? By definition, that is the limit as delta x approaches 0 of delta y over delta x. It's the limit, as our 2 points get arbitrarily close, of the slope. Rise over run. Delta y over delta x. Good?
Yep.
Now, I'm going to take that delta y over delta x, and I'm going to multiply it top and bottom by delta u over delta u. Delta u is how much our function g changes when we have a changed delta x.
Okay.
Right? It's the exact same thing I did up here.
Oh, I see that now.
Same thing,
Yeah.
multiplying it top and bottom by delta u. Swap our denominators here, and split our limit up into 2. So, that is going to be the limit as delta u approaches 0 of delta y over delta u, times the limit as delta x approaches 0 of delta u over delta x. You see it?
Yep.
Swap the denominators and split it into 2 separate limits. Perfectly valid. And now, what is the limit as delta u approaches 0 of delta y over delta u? That's the exact definition of the derivative of y with respect to u. And what is the limit as delta x approaches 0 of delta u over delta x? That is the exact definition of the derivative of u with respect to x. It's a lot more concise in this type of notation, which is why this notation shows up so much.
Yeah.
Okay.
But it's saying the exact same thing that we're saying up there, just different notation.
Yeah.
And if we went even further, well, I'll say this after we do an example with this notation. All right, so we've done this one. We haven't done this one yet, so I'm going to do this one using our new notation.
Okay.
Okay? So I am going to say, I'm going to recall this y of t just so we don't get confused. So I'm going to say y of t is equal to cosine of t squared plus 1, right? And we're looking for the derivative of y with respect to t. I'm going to say that u of t, I'm just going to write y equals, we won't do y of t, we'll just do y equals that. U, I'm going to say is equal to t squared plus 1, right?
Okay.
So y can actually be written as cosine of u. Y is cosine of t squared plus 1, but u is t squared plus 1. So y is also just cosine of u.
Oh, okay. Yeah.
They're saying the same thing, right?
Yeah.
So now, what is the derivative of y with respect to t? According to the chain rule, it's the derivative of y with respect to u times the derivative of u with respect to t. And what is the derivative of y with respect to u?
Cosine.
What's the derivative of cosine?
Oh, it's like sine, negative sine.
Negative sine. So the derivative of y with respect to u is the negative sine of u. And we got to multiply that by. What's the derivative of u with respect to t?
The derivative of u with respect to t.
Uh-huh.
It's just 2t, isn't it?
It's just 2t.
Oh, because it, okay, gotcha.
So 2t. Now finally, we don't want a u to show up in our final answer, so substitute back in whatever our u was. It was t squared plus 1. So this is equal to negative sine of t squared plus 1 times 2t.
Smart. Yep, that
Right?
makes sense.
Let's do the problem again, this time without overthinking it like that. I'm just going to do the derivative of the outside times the derivative of the inside. So, resolving the problem now, just looking at directly, not labeling all our intermediate steps. So what is x prime of t? That is equal to the derivative of the outside. What's our outside function? Cosine. So what's the derivative of cosine?
Negative sine.
So it's going to be negative sine of whatever our function had inside of it, t squared plus 1, times now the derivative of the inside, 2t. So you don't need to go through all this labeling, but it can help. Now, what happens if we have a function inside of a function inside of a function? It's the same concept. So if y is equal to some function in terms of u is equal to some function in terms of w, and w is some function in terms of x, then the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to w times the derivative of w with respect to x. Now notice that algebraically it's somewhat satisfying looking at that equation. It's not technically correct to do this, but it's good for your intuition to see. You can cancel out that du with that du, that dw with that dw, and you get dy dx. One of the reasons we like that notation. It's very,
You can't actually do that though, right?
it's not valid to, this is a symbol of something, it's not a quotient. But later we'll work with something called differentials, which are closely related, and it is valid to do with differentials. So,
Oh, okay.
we're not there. Technically, no, this isn't okay. But almost everyone thinks about it like it is okay. And if this didn't happen, you definitely did something wrong. That's for sure. Okay. So now, let's do another example. This time we'll do it, we're going to do it with 3, and so I'm going to do all the labeling. So, here is our function. I've got the tangent of the sine of 2t.
Okay.
So I'm going to call my most inner function w. So I'm going to say w is equal to 2t. And then I'm going to say my next most inner function, u, is equal to 5 minus sine of w. And then I'm going to say y is equal to the tangent of u. Or I could have gone the other way. Maybe that was a bad way to do it. Let's go outside to inside. Maybe that's most helpful. So our outermost function is tangent of something. So I'm going to say y is equal to tangent of something I'm going to call u. U is equal to 5 minus the sine of something I'm going to call w, and w is equal to 2t. You with me so far?
Good.
Now we are looking for the derivative of y with respect to
Why?
the derivative of y with respect to
T.
t.
Oh.
T is what it ultimately depends upon, right?
Yeah.
And so dy dt is equal to dy, the derivative of y with respect to
Derivative of u.
the derivative of y with respect to u times the derivative of
U.
u with respect to
W.
w times the derivative of w with respect to t. And notice you get all the crossing that you want. Okay. So what is, here's y, what is dy du? What's the derivative of y with respect to u then?
Negative cotangent.
No. What's the derivative of tangent?
Secant.
Secant squared. So you're going to ultimately need to memorize the derivative of your trig functions.
Yeah.
They come up a lot. Okay, next one, here's u. So now what's our derivative of u with respect to w? Equal to
Cosine of W.
minus cosine of w.
Oh,
Why?
What's the derivative of sine?
Cosine.
Cosine,
Oh.
but it's still negative.
Alright, gotcha.
And then finally, what is the derivative of w with respect to t?
2.
Just 2. So now I'm ready to write all this. So dy du is secant squared of u, right?
Yeah.
What is u? U is
Negative cosine.
5 minus sine of w, which is 2t. I'm just plugging it all back in now. So here is dy du. I just rewrote put my u back in.
Okay.
Good? Times du dw. What's du dw? Du dw is negative cosine of w, which is 2t, times, what's dw dt? 2. Right?
Yeah.
And now this one, I don't know, this one we can probably multiply out and get a prettier answer. So, do one of you guys have your book out?
Yeah.
See if you can find this example just to make sure we get the answer right.
It's in 3.5.
We're in the chain rule, so
6.
it's going to be example 1, 2, 3,
3,
example
7.
4, I think,
Yep.
in 3, 7.
7.
But, well, I don't know how else we can write that, so I'm just going to write that as negative 2 times cosine of 2t, all times the secant squared of 5 minus sine of 2t. I probably have it written something like that.
You said it was a fourth example?
I'm guessing, unless for some reason I skipped an example.
Oh, yeah, I see it.
It was right.
Well, it's equal to negative 2 times the cosine of 2t times secant squared of 5 minus sine of 2t.
Okay, yeah, we did all right. Okay, now once again, nobody actually goes through all this labeling, but you can do it if it helps. How do we solve this problem? We simply look at it and we say the derivative of the outside. What's the derivative of tangent? Secant squared. So secant squared of whatever that had inside of it. In this case, 5 minus sine of 2t. Now we multiply by the derivative of the inside.
Okay.
What's the derivative of the inside? Well, 5 is nothing, so we get negative sine of 2t. So what's the derivative of negative sine of 2t?
Negative cosine would.
Times, that would be negative cosine of whatever it was inside. But we have to use the chain rule now when we calculate our inner derivative. Times the derivative of 2t is
2.
times 2. And so we get the exact same answer.
Oh, what the heck?
So you can just think about it as taking the derivative of your inner functions, working your way in closer and closer to whatever it is.
And then at the end, just multiply.
Now let me do one more thing just to show you. It's sometimes helpful to think about the fact that you can always use the chain rule. So imagine that you just had sine of x. How come we don't do a chain rule with this? How come I don't say, what's the derivative of sine of x?
It's got no parentheses.
Negative cosine of x.
No.
It's just cosine. It's just cosine of x. But now I need to multiply by the derivative of the inside. What's the derivative of the inside? So I took the derivative of sine times the derivative of the inside is 1. And so it doesn't change anything.
Oh. Yeah.
So you can think that you were doing the chain rule this whole time, if you want. It just so happened that when you do the chain rule, you're left with 1. Or you could have said times the derivative of the inside with respect to x. dx, which is 1.
Okay.
Good? Alright, let's do some more examples and then move on to our next one. So I think we've done all those examples, so on to this example. Oh, we did this one. Let's do this one again. Just looking at it, see if you can tell me what it is. So here it is. What's its derivative? See if you can just read it to me. 7
times 15.
Times
Times 5x 3 minus x.
times whatever we had
To the
Okay.
power 6.
to the power of 6
Times 13.
Oh, that's right. 15x minus
minus
15x
to the cube. What?
15x squared.
15x squared minus what?
Minus 4x.
4x cubed.
And there you go. All right. Next one. Let's find the derivative of this thing. Now you already know how to do the derivative of this thing. Right?
Yeah.
How do you do it?
I-
Quotient rule.
Yeah.
So let's calculate using the quotient rule first, and then find a way to calculate it using the chain rule. So quotient rule, how do we do that? We do the bottom,
Low D high.
low, times the derivative of the top. What's the derivative of the top?
0.
0, minus high, times the derivative of the bottom.
It's a 0.
What's the derivative of the bottom?
It is 3.
3. All over the bottom squared. Right?
Times, just 3. Oh, yeah.
Did I mess something up?
No.
No.
So low d high minus high times the derivative of the bottom, d low, square the bottom, and away we go. Okay, and what are we left with?
Negative 3 over 3x minus 2x squared.
Right?
Yeah.
Okay, now let's think about this in terms of the chain rule. If you're going to think about this in terms of the chain rule, a better way to write that, and a common trick, is to rewrite that as, that's the same thing as 3x minus 2 all to negative 1. That is what this is. You see that?
Yes.
So now,
Oh.
let's take the derivative of that with respect to x and see what we get. Using the chain rule, bring down the negative 1 times 3x minus 2. This is now to the power of
Negative 2.
negative 2. All times the derivative of the inside,
3.
3. Or in other words, it's equal to negative 1 times 3 is negative 3. And then put this back downstairs, so now it's at squared. 3x minus 2 squared. Same thing, right?
Why did you have to use the chain rule?
You don't. You can use a quotient rule, you can use a chain rule. It's just a common trick to rethink about it in terms of the chain rule rather than the quotient rule. So there's a lot of problems where that is a helpful way to rethink about it. A lot of times we don't like using the quotient rule because it gives us, typically we have to simplify our numerator and do some algebra up there. And oftentimes just using the chain rule can help us skip that step. Okay. Next one, we have sine to the power 5 of x. See if you can just tell me it.
4.
4, 5 times
Cosine. No, sine of x.
times sine to the power of what?
4.
4 of x. Now times the derivative of the inside.
Oh, yeah, that's right. Cosine.
Cosine.
What?
Let me rewrite this in a more telling way. Sorry. That is sine of x to the 5.
Oh. Oh.
Same thing.
Yeah.
So bring the 5 down, makes that 4. Multiplied by the derivative of the inside gives us our cosine. See it? Okay. And our last one, last example, this one. See if you can just tell me what it is.
-3, 1, subtract 2x, and then 2. -2.
All times -2. Good. Did I write it wrong?
Wait.
No, that's right.
That's good. That's good. That's good.
Okay. And of course you can multiply that out and you can say that's 6 times, or maybe the best way to write it would be 6 over 1 minus 2x all to the 4. Something like that. Same thing, right? Okay, that's it for the chain rule. There's a bunch of examples using it. Now you have another tool for calculating derivatives. Okay, our next section is called implicit differentiation. Implicit differentiation, and it's for when you're working with implicit functions. Notice that I didn't tell you up here exactly what y equals.
It equals x.
No, y squared equals x. So what does y equal?
1 has a
And so it's implied from this function that y is equal to what?
The plus or minus square root of x.
Y is equal to plus or minus the square root of x. That was implied from this function. It wasn't directly given to you. So implicit functions are functions where the function is implied what it is from what you're given, but it's not given to you directly.
Okay.
It's an implicit function. Make sense? Now, what does this function look like? For any value of x, there's 2 corresponding y values, so it's not really a function, right?
So 1 is 2.
But for any input, there's 2 possible outputs. So if I tell you x is 4, what are your possible values for y?
2 and -2.
2.
2 and -2. So if you come over here to 4, then you get 2 and you get -2. Right? Plug it. If x was 9, then you could get 3 and -3. If x is 0, y has to be 0.
Yeah.
Okay. So y is equal to plus or minus the square root of x. Let's calculate its derivative. What is y prime equal to then? Or dy dx? What does that equal? Let's just look at the case where y is equal to the square root of x. Well, square root of x, that's the same thing as x to the 1/2, right?
Yeah.
So then what does y prime equal?
Oh.
1
Equals 1 half.
1/2 times x to the
1 power. Or 1 half.
negative 1/2.
Yep.
Or in other words, if I'm going to put it in the denominator, then that's going to be 1 over 2 times x to the 1/2, or 2 squared root of x.
Oh, strange.
Right? And then if we would have used the negative case, then it would just put a negative sign
Could
there.
you rationalize that?
Well, that's fine how it is. But yeah, you could rationalize it and multiply top and bottom by square root of x. Typically, we only do that with our coefficients.
No, it would just be square root of x over 2x, right?
What?
If you rationalize it, it would be square root of x over 2x.
Yeah. But that's a better way to do it. Rather than having your x's show up in multiple places. Okay, so that's one way that we could have done this. And so y prime is equal to that, or it would be equal to negative that. It's equal to plus or minus this thing, right? If we would have done the negative case, then it would come out negative. So y prime has 2 derivatives. We say, what's the slope when x is equal to 1? What's the slope when x is equal to 1?
Plus or minus 1/2.
Yeah, it's 1/2 up here, and it's negative 1/2 down here.
Right.
That's 2 slopes at x equal to 1. Okay, so that's one way we could have done this right here. Another way we could have done it is we could have said, I'm just going to take the derivative with respect to x on both sides. Okay? So if this is equal to this, then the derivative of this with respect to x is equal to the derivative of this with respect to x. Rather than solving it for y first, I'm just going to take my derivative right now. So what is the derivative of y squared?
2y.
It's 2y times what?
0.
The derivative of y with respect to x. We have to do the chain rule. The derivative of the outside times the derivative of the inside.
It's 1, isn't it?
Well, no, we don't know what it is, dy dx. That's what we're trying to solve.
But if you're using the power rule, wouldn't it be 2y?
That's if we were finding the derivative of y with respect to y. Or if we were finding the derivative of this with respect to y. We're finding the derivative of it with respect to x. So it's the derivative of the outside, which is 2 times y, times the derivative of the inside, the derivative of y with respect to x, whatever that is. And this is equal to the derivative now of x with respect to x. Taking the derivative of both sides with respect to x. So the derivative of x with respect to x is 1. The derivative of y with respect to x is not necessarily 1. You can't just say that. The reason that that turns to 1 and that one doesn't is because we're doing it with respect to x, not with respect to y. Okay, so in other words, we get dx is the same thing as 1. I'm going to replace this with the y prime.
Okay.
So I get 2 times y prime is equal to 1. Divide both sides by 2y, and I get y prime is equal to 1 over 2y. What is y? It's plus or minus the square root of x. So this is going to be 1 over 2 square root of x plus or minus.
Where did you get plus minus?
If I'm going to plug in y. Sorry, what's my y? What does y equal?
Origin.
And I just put the plus minus in the numerator rather than the denominator so it would match that.
Yeah.
Make sense?
Yeah.
Okay, let's do another one. So our job is to find the slope of x squared plus y squared equals 25. First off, what is that?
Circle.
It's a circle with radius
5.
5.
Radius 5.
X squared plus y squared equals r squared. So our radius is 5. And where's our circle centered?
The origin.
At the origin. Okay? So this is a circle centered at the origin with a radius of 5.
Yeah.
We want to know, find the slope of this circle at the point 3, negative 4. So 3, negative 4 down here, what is our slope going to be? Positive something, 1-ish. My picture's lying, but should be in the ballpark of 1.
Okay.
Should for sure be positive. Now let's find the derivative. So we're looking for dy dx. That's what we're looking for here, right? Okay, I'm going to take this. I'm just going to take the derivative with respect to x on both sides.
Okay.
What is the derivative of x squared?
1.
1. Wait, no, it's not. It's 2x.
In respect to x, it's 1.
It's 2x.
We've been doing with respect to x basically this whole time.
It's 2x.
What is the derivative of x squared?
2x.
2x. Now you can think about it. If you want to apply the chain rule, it's the derivative of the outside times the derivative of the inside, if that helps. Plus, now we got to do the derivative of this. What's the derivative of y squared?
2y.
2y. That's the derivative of the outside times the derivative of the inside.
dy over dx.
dy over dx. dx over dx is very different from dy over dx. This one happens to cancel out to 1. This one doesn't. And what's the derivative of 25 with respect to x?
0.
0. So that's equal to 0. So dx is just 1. And dy dx I'm going to rewrite as y prime.
Okay.
Okay. So I've got 2 times y prime. I'm going to move this to the other side. So that's equal to negative 2x.
Okay.
With me?
Yeah.
Now divide both sides by 2y, and I get y prime is equal to negative 2x over 2y. Cancel out the 2 top and bottom, I get it's negative x over y. That's my slope. That's my change in y with respect to x. It's x over y. So what is my slope at the point 3, negative 4? 3/4. Plug in 3 for the top, negative 4 for the bottom. Negative times negative positive, we get positive 3/4. Based off of our picture, we knew it should be roughly 1. Obviously, my picture's lying.
Yeah.
Yeah.
So sanity check checks out. Good? Let's do another one. Let's find dy dx when I have this thing right here. So start scribbling up here. So taking the derivative of this whole thing. Take the derivative of both sides with respect to x. So first off, what is the derivative of y squared with respect to x?
2y.
2y times dy dx. Gotta apply your chain rule. The derivative of the outside times the derivative of the inside is equal to
2x.
2x, and you can think about that times dx dx if you want. You'll get to the point where that stops bugging you, but just so you can see the symmetry for now. Plus, what's the derivative of the sine of something?
Cosine.
It's the cosine of that something. Now, I have to do my chain rule though, but so times the derivative of the inside. What's the derivative of x times y with respect to x?
0.
1.
You guys are trying to do some magic thinking without thinking it through. I've got a product of two things. What is the derivative of x times y? Let's write that as a separate thing over here, just to make sure we're doing this correctly. What is the derivative with respect to x of x times y?
It's y times the derivative of x plus x times the derivative of y.
The first
Yeah, x
times the derivative of the second plus the second times the derivative of the first. Dx dx is just 1.
Okay.
Good?
Yeah.
So using our chain rule, we got to multiply this whole thing now by this. X times dy dx plus y, right?
Yeah.
And now, multiply it out. Come finish. Yep, you guys guide him.
Okay.
I gotta help her for a sec. Keep going.
Alright, let's be done by the time he gets back. Let's hurry.
Okay. 2x times dx over dx is 1. 2x plus cosine of xy times that. Who wants us to multiply it out?
I would assume so.
Okay, so let's work on that. What does that equal to?
Multiply.
So we have 2x plus
Cosine x. Well.
You got it?
no,
Oh, keep going.
not finished.
Replace all your dy dx's with y primes. That'll help.
Okay. So
Cosine of x times y.
oh, we did that, didn't we?
Times
Oh,
y.
okay. X times y times x times y prime
Yeah.
plus y. Alright. Does that simplify?
You're gonna multiply it all out. You gotta solve for y prime. So notice you have a y prime over here, and then you've rewritten that side of the equation twice, which is probably gonna give you a headache. So
Okay, so yeah,
rewrite your equation fresh.
2y times y prime
Times y prime
is
equal to what?
2x plus cosine of x plus y, x times y, times x times y prime.
Plus y.
Ooh, keep the plus inside the parentheses.
Mm-hmm.
You're gonna have to distribute all that out.
Okay. Minus 2y.
No.
No.
You can divide
Oh, I
both
can
sides by
divide
2y.
Yeah. my bad.
Don't do that yet. Okay, so common procedure. Get all the terms that have a y prime on one side and everything else on the other side. You're going to have to multiply this out. No way around it.
Oh.
Yeah, we can erase the example from.
Okay, how should I go about that?
You need to do this times that plus this times that.
Cosine of x squared times y squared.
Okay.
So 2y times y prime is equal to, your 2x is still your 2x, plus, now distribute that out.
Cosine of x squared.
No. Cosine of x times y times, cosine of x times y is just a term.
Okay.
There you go.
Times.
Times,
Times.
I would use
cosine-
dot. You're getting confused with your times and your x's.
So it's cosine of x times y times x plus cosine of x times y times y prime.
Yes.
Or, right?
Cosine of x times y x, yes, plus time, or cosine of x times y.
Times y prime. Right? Plus cosine
Of x times y.
of x times y
Is it plus
of
there?
y. Is that right?
Where'd you get the y out?
Okay. We went
So,
And that's a plus.
you did cosine of x times y times
x.
That should be times.
x times y prime.
Oh, that's one term.
Yep, that's one term.
So that's times x times y prime
Uh-huh.
plus cosine of x times y.
Okay,
Is that right?
that works.
Okay. So
2y times y prime.
that should be y is equal to 2x. It's still there. Plus cosine of X times y.
Or
times x times y prime.
Yep.
Plus cosine of it. Okay. So how do you simplify that one?
of x times y times
Alright,
y.
what do we do now? We gotta put all our terms with a y prime in it on one side and everything else on the other side.
So divide x times y prime.
Not divide, just
this by
subtract this term over here,
Okay.
right?
Oh yeah, we could do
You just put all your terms that have a y prime on one side and all your other terms
that.
on
Would
the other side.
dividing work also or not?
No.
No, do not divide yet. Rule number one, the term you're solving for, all the terms it shows up in, you move to one side, and you put everything else on the other side. Then you factor it out, then you divide.
Okay.
Standard procedure.
Cosine of x times y of x times y prime. That's equal to 2x.
Don't you need to subtract your two?
What happened to this term?
I just subtracted it. Oh, that's it. That's the times. I keep on forgetting it times.
We are going all over the place.
My bad. That should be divided by 2y.
Yeah, except for
y.
why would you do that right now?
Oh, fair enough, I guess. Okay.
We'll have to reset up this problem.
Yeah.
Good that I'm making you guys do this because wow, you are struggling with your algebra.
Is that right?
Yes.
That looks correct. And now we'll divide by 2y.
What did we start out with?
Just divide by y?
Yeah, okay, that's right.
So we started out with
Where's my y prime? Where's my y prime?
y squared is equal to x squared plus sine of x times y.
Alright. And now.
So now I have to divide by 2y.
Hold on. Why do you only have one term on that side?
Not you.
No, over
On this
here.
side?
You should have this term.
I have that term. Right here.
Minus, there's a minus sign right there.
Oh, that's
Yeah, I wrote it a little.
that's a minus.
Yeah.
So you do have two terms on that
I
side.
had 2 terms.
Okay.
So now I can divide by 2y. Right.
Now factor your y prime out of your left-hand expression.
How do I do? How do I
It
do
shows up in both terms.
y prime times this. Or my.
I have a y prime in this term,
Uh-huh.
and I have a y prime in this term. So I can factor the y prime out of both terms.
Okay.
If I have a times b plus a times c, I can rewrite that as a times b plus c. You have parentheses around that x times y, but those aren't x times y prime, but that's not doing anything. You can multiply in any order you want. So you can think about that as just times that times that. So you can put the y primes first in this term if you want. You can think about it as y prime times x times.
Y prime times 2y subtract
So you still have 2y in that one. Yep. Minus
minus cosine
Cosine
of
of x.
x
cosine of xy
times x.
times x.
Times,
Good.
Yeah.
No.
No?
Because now you're trying to factor the x out of that. You can't do that.
Oh, that's right.
So parentheses have to go after the x. Good. Is equal to whatever you have over there.
Okay.
And now you can divide both sides by whatever your y prime is being multiplied by. And you got your y prime isolated.
Okay.
Oh, yeah.
Yes.
minus cosine
X times
x times y times x. I'm running out of room.
Yes, you are.
y minus cosine.
Okay, is that?
There it is. No, no, no.
That doesn't simplify out?
What's
No.
positive?
What
oh,
you were
what's
trying
positive? My bad.
And
that has nothing to do with it.
Really?
That is
How does
not
that
a
not
common factor. You can cross cancel common factors of the numerator and the denominator. I cannot take
Oh,
1
you're
plus
right,
2
you're right.
and look at 2 plus 2 and go, oh,
Okay.
it's a half.
Yeah, okay, that makes sense. Okay, so how do I simplify that? Does that simplify anymore?
No, that's probably the answer. Let's see. Read to me what you have.
Y prime is equal to 2x plus cosine of x times y over 2y minus cosine of x times y times x.
Yeah,
That's the answer.
That's
we're a little bit differently. All right.
Okay.
So I'm going to resolve this problem so that we can see all the algebra.
Okay. Just finish this real quick.
Yep, that's fine.
Minus cosine.
And then give you some common practices. Okay, so doing this whole problem all over again for the people on the camera. Derivative of the left-hand term. What's the derivative of y squared?
2y
2y times
y
dy
dx.
dy dx, which I'm now just going to call y prime,
Okay.
is equal to
2x
2x
y prime
times x prime, the derivative of x with respect to x, which is 1, so we don't need to bother writing it, plus
Cosine
cosine
of x times y.
of x times y times
y.
product rule.
Or
The derivative, the first times the derivative of the second,
So
the
x
first times the
2y.
derivative of the second, plus the second times the derivative of the first. You with me?
Yeah.
okay.
Okay, so now I get that that is equal to, we have 2x plus x times y prime times cosine of xy. So I'm going to rewrite that as the y prime first times x times cosine of xy. So that's multiplying this to this. The order that I multiply doesn't matter.
Okay.
Plus, I now need to multiply this to this. So that's y times the cosine of x times y. With me?
Yes.
Okay, now all my terms with the y prime go on one side, everything else goes on the other side because I'm solving for y prime.
Right.
So over here, I'm going to get
2y.
2y times y prime minus this term, which is going to be y prime times x times cosine of x times y, is equal to whatever we had left. We still have this,
2x times cosine.
plus y times cosine
Or yeah.
of x times y. Good?
Yep.
Now, factor out your y prime, and then divide by what's left. Maybe do it in 2 steps, I don't want to lose you. So y prime times, factor that out of both those terms. In this term, we're left with a
2y times
2y. And we get minus, what are we left with over here?
X times cosine of x times
X times cosine of xy is all equal to whatever we still had over here.
Yeah.
Okay, now divide. And so y prime is going to be equal to this thing, 2x plus y times cosine of xy all over 2y minus x times cosine of xy, which should be exactly what he has. As a matter of convention, put your other variables before your trig function,
Oh.
but perfectly valid answer.
Oh, yeah.
That's just convention. Okay, so there's doing that problem. All right, let's try another one. This time we're looking for the second derivative of y with respect to x.
Okay.
Good? All right, so first off, take the derivative with respect to x of both sides. So, what's the derivative of this with respect to x?
6x squared.
6x.
Perfect. What's the derivative of this?
Negative 6 at y.
Negative
6y.
6y
Times, wait, it's respect to x?
Not times.
with respect to x.
So it's times dy
Oh.
dx.
Times dy dx, which is
So
y prime, is equal to
0.
0.
0.
0.
And then you do it again.
I'm going to move this to the, we could do it again. I'm going to do some simplifying first.
Okay.
So I'm going to move this to the other side, but I'm going to write it first.
So y prime is equal
So 6y times y prime is equal to 6x squared. I move that to the other side, and then just rub this side first.
Oh, okay.
Follow me?
Why do you not isolate y prime?
Why is it?
I did. I isolated the term that had a y prime in it.
Because it's multiplying by 6y.
You're not gonna isolate it further?
Well, now we can simplify
Take another
and
derivative.
divide everything by 6, and I can get y times y prime is equal to x squared, right?
Oh, yeah, gotcha.
Or I can get y prime is equal to
X squared over y.
x squared over y. Well, that's what y prime is, but that's not what I'm looking for.
Now
I'm looking for
you
y double prime.
Derive it again.
So I need to take the derivative of both sides again. Now, I don't want to do a quotient rule. So I'm going to do it on this step.
Okay.
Because I'd rather do a product rule with these two than a quotient rule with that.
Okay.
But it doesn't matter. So working with this step, taking the derivative, I need the derivative. So I get the first times the derivative of the second. So the first times, what's the derivative of y prime?
It's
Y double prime.
Yeah.
It's the derivative of the derivative. That's what y double prime is,
okay.
right? So I got the first times the derivative of the second, plus the second times the derivative of the first.
Yeah, weird, yeah, okay.
Follow all that?
Oh, strange. Okay, yeah.
Is equal to
2x.
2x times dx dx if you want to think about that. Okay. And now we can rewrite this as, well, y prime times y prime, that's the same thing as y prime squared, right? I'm going to subtract both those over here. So I got y times y double prime is equal to 2x minus y prime squared. Like that. With me?
Yep.
Now, we know what y prime is in terms of x's and y's. I ultimately want my answer to be in terms of x's and y's. I don't want there to be y prime showing up in my final answer. So, I'm going to make that substitution. So I get y times y double prime is equal to 2x minus this thing squared. What is this squared? It's going to be x to the 4 over y squared. Right?
Can't you cancel out?
No.
Never mind, you can't do that.
Okay. And then so finally, divide everything by y, and I get y double prime is equal to 2x over y minus x to the 4 over y cubed. Just to make sure we didn't make any mistakes. 2x cubed minus, is that the right one? Yes. And our answer is 2x over y minus x to the 4 over y cubed.
Yep.
Okay, we did it right. Last one. One more example problem using all this. Our job is to find the tangent and the normal to this function at the point 2, 4.
What is the normal mean again?
The normal is the one that goes straight out from the curve. So I have no idea what this curve looks like. I'm going to draw a false picture just to give intuition. So maybe when we graph out, what curve? This one. Maybe when we graph that out, that looks something like, let's see, it goes through the point 2, 4. So maybe it looks something like this. I have no idea what it looks like. Right? Some curve. If we're looking for the tangent and the normal at that point, that means we're looking for the tangent line that goes through that point, which would be the red line, right?
Yeah.
And then the normal one is one that's perpendicular to it. That would be the normal.
Okay.
The one that points directly up from it. Make sense?
Mm-hmm.
So we're looking for this line and this line. What are those lines? Now,
Oh, the tangent line is the derivative of that.
right, so the tangent line has a slope equal to dy dx at this point.
The derivative of it. Okay.
Yes. dy dx. Make sure we're doing dy dx, not dx dy. Because there's no reason that you couldn't do dx dy if you wanted to. I could differentiate this whole thing with respect to y. I get a different answer. That's giving me the change in x with respect to y, which isn't what we want. We want the change in y with respect to x. We want rise over run, not run over rise. They're different numbers. I could do dx, dy if I wanted to, if I cared about that for some reason. But we care about rise over run in general, not run over rise. But you could do run over rise, and that would be dx dy, and it gives you something perfectly fine. Okay, so I need to find dy dx or y prime. That will give me my slope at that point. So let's find dy dx. I'm going to differentiate with respect to x on both sides.
Okay.
Tell me what to write.
3x
Squared plus 3
y to the cube.
squared, you bring down the 3, which
Or
squares it,
squared, not cubed.
times y prime, or dy dx, minus 9 times
X
Where's
times
this
x
from?
prime or y prime. Is that right?
almost,
Well, okay. So
missing the second half,
and then
plus
y
the first times the derivative of the second, plus
plus y x prime.
times derivative of x with respect to x is 1.
Oh.
Because we're doing the derivative with respect to x, right?
Yeah.
Yeah.
So product rule, and this is all equal to,
Wait, isn't that negative 9 plus x times y?
I just factor out the negative 9. The derivative of a constant times some function is the same thing as a constant times the derivative of the function.
Oh.
So I just pull the negative 9 out.
Oh. Okay, that's right.
I see.
But it multiplies back in when it's all said and done.
Yeah.
Well, okay.
Let's think about it this way. Maybe here's how you're thinking about it. Let's think about negative 9x as the first one and y as the second one. So then that would be the first times the derivative of the second plus the second times the derivative of the first. The derivative of the first is going to be negative 9, so that would make this a negative. And this would be multiplied by 9, right?
Oh, okay.
And then if you factor out the negative 9, you're left with x times y prime plus y.
Yeah.
Okay.
So,
I see.
works out either way. Should be more explicit when I do stuff like that, but yeah, good practice to factor out the constant first, then deal with it so that you don't have to carry the constants around everywhere, because you're most likely just going to factor them out when it's all said and done anyways. All right, and this is equal to
0.
0.
Oh, yeah.
Derivative of 0 is 0. Okay, so what are we solving for?
We're solving for
Tangent.
y.
We're solving for y prime here. That gives us our change in y with respect to x.
Oh.
That's what y prime is.
Right.
That's what gives us our slope. So, I'm going to take all my terms that have a y prime in it, and I'll keep them on the left, and all the terms that don't have a y prime in it, I'm going to shove to the right. You have a y prime, you get a stay. Negative 9 times that, you get a stay. This term, you got to go.
Or the other one.
And negative 9y, you got to go.
Yeah.
With me?
Yep.
Now just divide through everything by 3 really quick, just cause. Actually, I'm going to divide everything by 3 and factor out my y prime over here at the same time. Let me do 2 steps at once. Tell me if I'm losing you in the algebra. You okay with everything I did there?
Yes.
I factored the y prime out of both those and divided everything by 3.
Okay, yeah,
Good? All right, now we're solving for y prime, and so y prime is equal to negative x squared plus 3y all over y squared minus 3x. Right? Now we were looking for the slope at a particular point.
Oh, 2, 4.
So at the point we care about, our slope, I'll call it m, is equal to what? What are we plugging in for x squared here? 2, so negative 4
Plus 12 over 8 or 16.
Okay, negative 4 plus 12 is
18.
all over,
10.
which is equal to 4/5. So that's our slope of our tangent line here, 4/5. We are looking for our tangent line. So I'll do y with the subscript here t to let us know it's our tangent line, so we don't think it's the same y that we're using over here.
Okay.
Coming up with the equation of that tangent line. What is the equation of a line that has a slope of m and goes through a point 2, 4?
Y1 minus, or it's Y minus Y1.
Y minus y1, what's our y1?
4.
4
Is equal to
m
is times x
times x
minus x1.
minus x1. Good?
Yeah.
That's the equation of our tangent line. The equation of our normal line. Notice our normal line goes through the exact same point, but what is its slope compared to this one's slope?
It's negative. It's something.
Let's
Is it not?
let's come up with some intuitive examples.
Isn't it?
So let's say that my arm has a slope of about 1/2.
Okay.
What would the tangent have a slope of? Or sorry, what would the normal have a slope of?
The negative reciprocal.
And not.
Negative 1/2 would be like that.
It's a
Oh,
negative
it's negative
reciprocal, isn't it?
Negative 2.
Oh.
So that's going to be.
So if your tangent has a slope of m, your normal has a slope of negative 1/m. Negative the reciprocal.
Okay.
That make sense?
Yeah, that makes sense.
Yeah.
Okay, so here, our normal line, it goes through the same point, so it's still y minus y1. All that changes is our m here. And instead of 4/5, it's what?
Negative 4.
Negative 5/4. Negative reciprocal. Negative 5/4. Times x minus 2. And then solve each of these to get exactly what it is. So y sub t is going to be equal to 4/5 times x is going to be 4/5 x, right?
Yeah.
Yeah.
And then we're going to have 4/5 times negative 2
Is 1 and 3.
is negative 8/5.
Yeah.
And then we're going to have plus 4.
Yeah.
Moving the 4 to the other side. Good? And so finally, that's going to be equal to 4/5 x plus what?
17 fifths.
No. 4 is the same as how many fifths? 20. 20 minus 8/5 leaves us
Oh, it's a minus.
12/5. Good?
2. Yeah.
So that should be our tangent line. Our normal line, what's our normal line? That's this one. So y sub n should equal, we got negative 5/4 plus 10/4, right? Oh, sorry, I missed my x. Thank you. That's what you were saying. Plus 10/4, and then move this to the other side. Plus 4. Right?
Oh, yeah.
And this is equal to, we can say negative 5/4 x.
50 over 4.
10/4 plus
26 fourths is what it should be.
how many fourths is 4?
16.
16 plus 10 is
26.
26. Oh, is that what you said before? I heard 56. Okay. So 26 over 4. Trying to get you to do it on your head, but do it one more time. What goes into both of those?
2. It's
2.
13 halves.
13 halves. There you go. So let's double check. I'll read what the author has, check it with the whiteboard so I don't have to look back and forth. So for one of them, he has y equals 4/5 x plus 12/5. And for the other one, he has y equals negative 5/4 x plus 13 halves. And that's it.
Oh.
So I think you guys are okay with the calculus. I think the algebra is going to come back to bite on this homework a lot.
Yeah.
Algebra-lysis.
But yep, that's it for material. So you have the rest of the class to start going on your homework. Do whatever you would like.
Thank you.